then later you upload it to the drive. Okay, let's start with the 21st session. So this is on Bayesian optimization. So before I start off with these slides, I just thought of sharing a small real life story on Bayesian theory. So this is a bit connected to Netherlands, Ukraine, and Russia. So I just thought of sharing this so that it will be a kind of interest to all of you. So I guess like almost 8 years ago, in the year of 2014, there was a Malaysian airline which was traveling from Amsterdam, and it was supposed to reach to the capital city of Malaysia, Kuala Lumpur. So, but it never happened because when the flight reached the airspace of Ukraine, it was shot down by a Russian made surface to air missile. So because of this, around 298 people who were in the plane, everyone was killed. So later, the Forensic Institute of Netherlands, it was supposed to quickly identify the dead bodies, and it was supposed to give them to the respective families. So because of there would be a lot of pressure in dealing with these processes, and it should be very quick. And apart from that, since there was a conflict that was going with Russia and Ukraine, the forensic team was having very limited access to the crash site. So it was difficult for them to collect the DNA samples from the crash site and later identify the dead bodies and giving it over to the families. So at that particular point of time, there was a state-of-the-art disaster victim identification program. So this was called Bonaparte. So like this software was developed in 1990s or 2000s, but the core part of the software was using Bayesian networks to combine DNA information, which was taken from like the different family members of the victims, and later which would collectively help in identifying the victims of the corresponding family members. So because of this particular state of this art software, uh, the forensic team was able to identify 294 of 298 victims. So it anyways took 6 months, but still they were able to do all of these in that 6 months, and they were able to close this case. So this was a small real life incident I just thought of sharing with you.
Which year did you say again? I mean, the year
2014.
2014. Okay, nice.
Yeah. Okay, let's go ahead with the presentation. So here I'll be discussing in brief like these topics, the hyperparameter optimization, and later on I'll touch upon these surrogate models and acquisition functions. So this will be a kind of interactive session. So I would be asking few questions so that everyone is alert and listening. I know it's afternoon for someone, so they might be dozing off if the topics are boring. So I'll ask a few questions so that everyone will try to think and answer. Okay. So in ML and DL model, so like you would be having these two kind of separation between hyperparameters as well as the parameters. So basically parameters of the model are the ones which are learned during the process of training. So by once you give the training data, the weights and biases would get updated based on the back propagation algorithm optimization process. So this is where the parameters would get updated. So obviously it is not under the control of the data scientist. So he can never modify or tune it during the training process. So it is because these are the weights and biases that are getting learned, and these are the brain of the model. So similarly, there are hyperparameters as well, which are the ones which you can tune during the training process. So basically, the objective function, like suppose you are supposed to minimize the error, then based on the hyperparameter combinations that you choose, these backpropagation or optimization methods will try to converge to the local or global optima. So basically, it completely depends on the kind of parameters that we choose. So here, there are a couple of algorithms. So initially, it started with random search, and initially it started with grid search, and later on, to improvise the results, and instead of keeping the search space deterministic, it was transformed or translated to a random combinations of the hyperparameters using random search. So in that case, results improved a bit compared to grid search, but still these two approaches were not giving the best results, because it is just like beating the bush. Wherever it feels like taking the parameters, it will choose them and try to compute the objective function for those set of parameters. So basically, the thing that was lacking with these two algorithms was there was no improvements that were happening iteratively with each and every search step. So because each of these search parameters, the way they were selected at each iteration was independent, but it has to be dependent on each and every step, because evaluating the objective function is complex and tedious process. It is a very costly process actually. So if you take a deep learning model, a very big model, so if you are not learning in which direction you are going in the optimization process, so for a set of hyperparameters, it will take a lot of time. So as you know, it will take hours together to train a particular model for a particular set of hyperparameters. So if the algorithm does not learn in which direction it is going, whether it is correct or not, then it will take a lot of time, and it is no good than a trial and error process. So here, as I mentioned before, the goal is to find the best hyperparameters. So here, suppose this is the function, suppose this is the loss function. So here we are supposed to get the combination of hyperparameters, that is x star, for which this loss function, suppose this is a mean square error, is minimum. So that is the prime objective of this hyperparameter optimization. Okay. So in Bayesian optimization, there are two different concepts, that is surrogate model, and the second one is acquisition functions. So I'll discuss a bit more on these two concepts before all these steps are merged in Bayesian optimization. So the first thing is the Gaussian process. So if you are aware of stochastic processes, so Gaussian process is one of the stochastic process, which is having infinite dimensional Gaussian distributions. So it is basically like if you are aware of multivariate distributions, suppose you are aware of suppose there is one random variable and it is following a Gaussian distribution. Then I guess it will be better I use. Okay. My screen is still visible, right?
Yes.
Yeah.
Yeah, we can still see it.
Okay. Suppose there is one random variable. So it is following a Gaussian distribution. Now I take two random variables. So the first one, you can say this as a univariate distribution. The second one, it will be, suppose if there are two random variables x1 and x2. So when there is a joint distribution between these two random variables x1 and x2, so in 2 dimensions, this is how it is going to look. So when you slice this at any particular instant, like this in x direction or y direction, you can see the slice will appear something like this. So this is multivariate distribution. So here there are, since there are 2 random variables, like this will be a bivariate distribution. So in multivariate distributions, this is a combination of several random variables. So in Gaussian process, since I mentioned this is infinite dimensional Gaussian distribution, so it is much beyond multidimensional, multivariate. So multivariate is greater than 2, but it has a finite number, right? So in Gaussian process, this is an infinite number. So there are infinite number of random variables which can be modeled using Gaussian process. So as it is mentioned over here, it is a collection of random variables. Any finite number of random variables have a joint Gaussian distribution. So that is, suppose I draw a 10-dimensional, suppose this is some Gaussian process, which is a 10-dimensional distribution. So in this 10-dimensional distribution, if I choose any 2 points, and plot the distribution, this is how it is going to look for these 2 points, the joint distribution of these 2 points. And at each of these points, the distribution will be like this, because each and every point is a Gaussian distribution. Any questions on this? Are everyone on the same page?
Could you just repeat that last, the third graph again?
Okay, so the third graph is a Gaussian process. So this Gaussian process, suppose I don't take this as a 10-dimension, I'll just make it simple. So since I have drawn 1, 2, 3, 4, 5 points, so let this be a 5-dimensional Gaussian distribution, Gaussian process. So each of these points, so 5-dimensional means there are 5 random variables. So each of these points correspond to a random variable. Okay, so here this is x1, like that, x5.
And what will be the y-axis here?
Y-axis is similar, like the probabilities.
Probabilities, okay.
Yeah. So here as well, x-axis is the values, and the corresponding probabilities are represented here, right? Probabilities.
Yeah, but I mean in the bottom one is also probabilities.
Yeah.
But not in the second one, because in the second one, the circles represent the possibilities,
Yeah,
right?
here, this, like, since I'm visualizing this in 2D, but if you visualize this in a 3D, right? It is difficult to draw here.
Yeah, but the second one is basically if you would look from above, right?
Yeah. The third axis, z-axis, will represent the probabilities in second one. Okay, so the third one, since this is a Gaussian process, so this is a 5D. So like this Gaussian process has been drawn based on these interaction of 5 different random variables. So this can be any dimension, like you can draw 100 dimensions, 200 dimensions, in like 1,000 dimensions. So what that means is 1,000 dimensions of a Gaussian process means there are 1,000 random variables, and the Gaussian process is being sampled from those 1,000 different random variables, and this process, this line has been fit based on those random variable interactions. So that's what essentially it means. And when you take each of these points, like it'll be a Gaussian distribution with a particular mean and a covariance matrix. Got this right?
Yes.
Okay, suppose here there is another example. This is a 8-dimensional Gaussian. So you can see there are 8 random variables. So when you create when you define the mean and covariance matrix for this 8-dimensional Gaussian and try to sample from that particular Gaussian process, this is how different samples look like. So in each of these samples, so we call each of these curves as a realization of a Gaussian process. So you can see the 5 samples are 5 realizations of the Gaussian process, which are derived from the Gaussian distributions. So in this small video here, you can see, suppose I have defined the mean of this Gaussian process to be 0, and there is some standard deviation that I have defined. So when I try to sample from this particular Gaussian process with mean 0 and a certain standard deviation, so here you can see these are different realizations that are getting sampled from the Gaussian process. This is how it looks like. So it is basically the same which is described in the right side of the diagram, but it is limited to a particular mean and a standard deviation. So always you can see the lines over here, right? The upper and the lower confidence bounds, which is shaded out in gray area. So that basically specifies the variance of this Gaussian process. So here you can see this mu plus 2 sigma and mu minus 2 sigma. So most of these samples that are getting sampled from this Gaussian process will, at most of the times, it would stay in these lower and upper bound limits, because those are still following the same mean and covariance matrix that has been defined before. Any questions over here?
No.
Okay, and one more thing that I wanted to specify is here I'm using a RBF kernel. So you would be heard of Kirtana taking this name RBF kernel when she was doing experimentations on SVMs. So RBF kernel is a non-linear kernel. So whenever the data is very complex, and it is not linearly separable, we try to use this RBF kernel to transform the data from lower dimensional space to the higher dimensional space. So once we transform the data into a higher dimensional space, then we try to compute, using this RBF kernel, we try to plot these distributions. Suppose to get rid of these. Suppose the linear separability can be defined in SVMs just by these points. So this is a very simple data, and you are able to separate these labels with just a linear separation hyperplane. Suppose the data is not linearly separable. Suppose you are having points like this distributed in circular fashion. So when the points are distributed in circular fashion, then when the linear hyperplanes is not able to separate this out, then we use RBF kernel. So the RBF kernel, since it is following a Gaussian distribution, this will transform these circular points in a higher dimensional space, and this will make it look like the hyperplanes get separated using these 2 circles because of this RBF kernel in SVMs. So that's how the separability works out in SVMs using complex kernel functions. Okay, so since I have given this example in the previous slide, I wanted you all to think and tell me approximately what could be the answer for the question 1. So this is a Gaussian distribution with the mean and the variances like standard deviations. So how much area under the Gaussian curve is occupied by this block, mu plus or minus sigma, and mu plus or minus 2 sigma, and mu plus or minus 3 sigma. So I wanted you all to think and tell me what will be the answer for this.
I know there's a specific answer for each of these points, but I forgot what the percentage is. Something in me says 34%. Is that a
34% for what?
yeah, so that's what I don't remember. I remember seeing this graph and then seeing the percentages of how much area is under the curve,
Yeah, it's
but
like,
I forgot what it was.
Okay.
it's like the third one is around 97% of something.
Third one in the sense, which one? Mu plus or minus 3 sigma, right?
Yeah.
Okay. And what about these two? First two?
I know one of them is 60, 67 or
Okay. And so which is 67?
I think the first that the first mu minus to mu plus covers around 67% of.
Okay. And any random guesses for the middle one?
I don't know, it will be in 70s,
Yeah, I would say in the 70s as well.
70s or 80s, 83%.
Okay, fine.
Are we not close?
Yeah, like first and third is correct. So mu plus or minus sigma will cover 67 to 68% of the curve. And mu plus or minus 3 sigma will cover 99.2%. The second one, the mu plus or minus 2 sigma will be covering 95%.
Okay. Both of them are 90s only.
Yeah, 95 and 99.2.
And
So
what was the first one?
can you come again?
What was the first one?
First one is 68%.
Okay.
So
yeah, then the 32, the 34 or 32, where I was thinking was probably what is outside of the curve then.
I guess you were just telling about this half curve.
Yeah, could also
Yeah.
be, yeah.
Yeah. Okay. So like all of you would be aware of 95% confidence intervals, right? You would have seen this term very frequently. So what that means is it is basically the mu plus or minus 2 sigma of this normal distribution curve. So when I draw, yeah, in this diagram, I guess it is better to take other thing. Machine process, I guess. Okay, yeah, here it is mentioned. Yeah, so this is like the mean 0 and mu plus or minus 2 sigma curves that I have drawn over here. And for these specific data points, this is a Gaussian process regression that has been fit for these points. So what this thing like I have mentioned over here is like these confidence bounds, the upper and lower bounds are mu plus or minus 2 sigma. These represent the 95% confidence intervals. So what this means is whenever I try to draw a realization of this Gaussian process, 95% of the times it would stay in these limits of lower and upper bound. So there is 5% chance that it might go beyond this particular curve. Suppose like this. So this is what it means. Like there is a 5% chance that the sampled distribution in this Gaussian process can go beyond 2 sigma, and 95% of the times it will remain in this curve itself. So here you can see 95% of the times it is under the curve. So here you can see very less probable situations where it is going beyond the limits. So that's what it means actually. Okay. So since you said or like at least try for other question first, can you try the same for question 2? So how to find the area under the curve and interpret the same. So basically like I'm asking, so how do you like you know the PDF and CDF, right? Probability density functions and cumulative distribution functions. So what does like each of those mean, like PDF and CDF of a particular distribution? It can be any distribution, uniform or Gaussian, anything.
Sorry, I'm like, what are you asking? Like, what do you mean by distribution function? Is it?
No. What do you mean by like a probability density function and cumulative density function? Suppose like in this distribution, right? I tell like this mu plus sigma value is 5. Okay. So I want to find what is the probability of occurrence of this particular value 5. Given that I have, my distribution is Gaussian. So using which can you find out, like using PDF or CDF, and how do you interpret that? Meanwhile, I'll open that as well.
I know that one of them is like calculating something like the area below the curve, but I am like totally blank.
Yeah, I think you can see the answer in the second one on the right.
Yeah. So at least with this hint, can you try?
Yeah, I vaguely know how to do it, but I
Oh,
forgot
okay, yeah,
the
got it,
exact
got it, got
functions.
it.
Yeah, you can use the point on the x-axis to determine where that cutoff line is, and then you can calculate the area that is on the left or on the
Okay.
right.
Like a CDF would have like just one limiting thing, and PDF will have like both x less than 0, greater than 0, something like that. It'll have two margins. And
Okay.
having just one, but
Yeah, formula wise fine. So how do we interpret this?
how do we interpret?
Suppose, okay, in the interest of time, it is already half an hour. I'll start this. So suppose you are having a dice. So it is usually you'll be having 6 numbers. I just put it over 5 here. So so in the dice when you throw, there is a probability of since there are 5 values over here, it is like 20% of the times you have chance that you get 1 or 2 or 3 or 4 or 5, right? So this is a uniform distribution. So this is a PDF actually. So if when I ask you what is the probability of getting 3, the answer is 1/5. This thing you are getting from the PDF. So like this is a discrete random variable function. So when this is a continuous function, suppose like this thing. Let me write it over here. Suppose it is a normal distribution only, and there are these
Can I do
intervals.
an attempt? I think I
Yeah.
know how to explain it. I think you can interpret it as given a number of x, what is the probability that we find a lower value?
I didn't get you.
So if you would look at the second graph, so given that you have the value of x, and then you can use this function to calculate the probability of finding a lower number. Oh,
Yeah,
does that
like
not?
no, like formula wise is fine. I just I'm trying to give an example over here. So let's say like they like a class of students with for a subject they have got some evaluation marks over it. So when you try to like arrange those marks in a like a increasing way over here, and it will be mostly following a normal distribution. Like so how to interpret this normal distribution for this example is, so there would be only less number of students who would have got very high marks, and there would be less number of students who would have failed. So most of the students concentration would be in the middle. So they would the marks would be in the middle. They would neither have failed or they would have not got distinction kind of marks. So this is how like we interpret this kind of a normal distribution. So when I ask what is the probability of getting this, what is the probability of getting students with the marks at maybe 70%. So when you plot this distribution and you see, suppose the 70% value is coming over in this region. So you try to find the area of this particular region, and that will be the probability that how much likely this 70% of the marks are got by the students. So that is the PDF. So always PDF is defined between intervals, that is A and B. And CDF means, suppose what is the probability of getting students who have attained 70 marks and below. So since there is no lower limit in CDF, so it just takes the cumulative of everything that is arranged before. So you will get a combined probability score of all the students who have got marks less than 70%. So here you take the area of the complete curve till that particular point X. So here there is only one limit. In PDF, you'll be having two limits. So here you can see in this DICE experiment, right? So the CDF, since it is increasing 20% in each of these iteration. So suppose if I tell what is the probability that of getting any number less than 4 will give the CDF. So it is 80%, right? So since there are 5 numbers in the dice, and probability of getting any number less than 4 is 80%. So that is what the CDF means. And probability of getting just the number 4 is 20%. That is a PDF. Any questions on this?
No.
Okay. Fine then. So going ahead, this is like the previous thing that I discussed. Gaussian process is the surrogate model concept that is in Bayesian optimization. So the next thing is multi-armed bandits. So here I want you all to think of this. So suppose you are given with these slot machines. So usually you would see all these kind of slot machines in casinos. So the basic objective over here is to play these machines and draw these levers as many times as possible, so that you are aware which slot machine is giving you the maximum reward. So basically, you are trying to find out which slot machine is giving the maximum reward, and are trying to get more money out of it. So here, each of these slot machines would be having certain kind of a distribution in which whenever you try to draw these slot machines, right, you will get some value out of it. So it is based on some distribution which is unknown to you. So you are just supposed to find out it by yourself. So can you all think of a strategy that you can follow to find the maximum reward in less amount of time?
The maximum reward from one machine, you mean?
Yeah. So usually out of, suppose you have 5 machines, there would be one machine which would be having the highest reward. When you draw that particular machine, it gives the highest reward. So how do you find out which machine is that?
I would say you sample all of them a few times, and then you can draw the distribution, and then you take the distribution that leans the most towards the right.
Yeah, drawing is still fine. Suppose you are in real time playing the slot machine, and you are supposed to make these decisions very quick. So yeah.
Gert, I'm not sure if you had the same course at the university, because I remember the example. I don't remember the answer, but it was that game theory from Peter Spronk. I'm not sure if you had that course.
Yeah, this is a game theory concept as well. Yeah. Anyone Kirtana, Joe, can you try to answer?
I think because you said you want to make it as efficient as possible, we're not going to pull the lever 10 times on each machine. That won't work because that's not really efficient, I guess.
Yeah.
So
Yeah,
then
slightly
maybe
moving ahead.
So then maybe, well, you have to start somewhere, and maybe if it gives a reward, then if it doesn't give a reward, you go to the next one.
Yeah, or probably something like you pull them all once, and then you just take half of the most rewarding ones, and then you pull them all once, and then you can cut it down until you are at the most rewarding one.
Yeah, right. So here, there are different probabilities over here, right? So basically, you are supposed to deal with the exploration as well as exploitation trade-off. So you are supposed to explore each of these machines. Apart from that, from whatever you have experienced after drawing the samples from each of these machines, based on your analysis, whichever slot machine has given you the highest till that particular instant, you are supposed to exploit that more. So that is the trade-off that you are supposed to leverage in this strategy. So you need to exploit new machines, as well as you need to explore, as well as exploit the ones that has already given you the maximum reward. So here, that is what these acquisition functions will do for us. So there are a couple of acquisition functions. This is one of them, probability of improvement. So here, this probability of improvement, this particular acquisition function, it chooses the next query point as the one which has the highest probability of improvement over the current maximum. Suppose this is a Gaussian process that you have fit, and you can see these black points, right? So these are the training points that you have till now. And suppose I define this x-axis as hyperparameter combinations and y-axis as accuracy. So here your goal is to maximize the accuracy, and you are supposed to find out for which combination of hyperparameters in x-axis you are getting the maximum accuracy. So in this unexplored space right now, initially you would not be having any of these training points, right? Because you haven't yet started the experiment. So at that point of time, we would just draw a Gaussian process as I showed it to you over here. So this is a prior distribution of a Gaussian process without any training samples inside it. So for this prior distribution of Gaussian process, we try to sample each of these points based on this acquisition function, probability of improvement. And once we get the accuracy for a particular combination of hyperparameters, we try to fit the Gaussian process again based on the training points that we have got. So in first iteration, we would have got 1 point. In second iteration, we will get 2 points. So we will try to fit the Gaussian process so that it passes through these 2 points. And in rest of the points, there would be a high degree of uncertainty. So you can see this shaded curve, which was the 95% confidence interval in the previous slides. So for points which you have already explored, the variance or the uncertainty will come down drastically. So here you can see there is very little variance at the points that you have already explored, and so much of uncertainty in the points where you have not explored. So this is what the acquisition functions do to find out which is the next point, potential point that I need to explore, so that the objective function, which is sitting in the y-axis, is having a maximum possibility of improvement. So here, suppose after 3 iterations, this is the maximum accuracy that I have achieved till now. So the probability of improvement, what it tells is, in the remaining of the curve here, you can see with respect to the current maximum that you have achieved, what is the probability of improvement that you can observe for the rest of the curve. So in the left side of the curve, you can see there is a very limited possibility because most of the curve is below the current maximum. In the right side of this point, you can see there is a potential possibility of improvement, because here you can see the Gaussian process. As I mentioned before, each of the sample in this particular line will follow a Gaussian distribution. So here, when you plot this, here you can see in this Gaussian distribution, the shaded portion is the potential improvement that you can observe with respect to the current maximum that has been achieved till now. So this is the CDF. So since you saw in that TIAC sketches, right? So this is how the CDF will look like, right? For you know this particular point, and you try to integrate the complete area and find out what is the potential improvement that you can achieve from the current maximum. So here in this formula,
Sorry,
you can see.
I have one question, Shreyas.
Yeah.
What if let's say you follow the line and the line goes back down, and then at some point it goes up again? Then would the green part be opposite?
Yeah, it would be opposite. Yeah.
Yeah. Okay.
So this is a very simple function. So in real scenarios, you can see a very complex functions with so many peaks and so many crests. So in those, it would be a bit challenging for these acquisition functions that they would get stuck in local minimas. So there are improvements of different versions of these acquisition functions, which are try to not fall in the local minimas and try to get the a global minima as much as possible in less iterations. So here probability of improvement, it is just giving you the probability, but it is not giving you the exact value. Like in PDF, that I mentioned before, right? You are getting the exact value, like what is the probability of getting 4? You know that it is 30% or 40% or 10%. You know the exact value. In CDF, you are not getting the exact value. Instead, like a probability of getting the number 4 is 80%, but it is just a probability, it's not an exact value, right? You can achieve it or not. So that is one of the disadvantage of probability of improvement. So the next advancement over probability of improvement is expected improvement. So here the basic difference is, as I mentioned, in PI, it considers only the probability of improving the current best estimate, but it does not find out how much magnitude of the improvement can be observed actually. So we basically do the expectation of the improvement that was achieved in PI, and we try to get the value of expected improvement. So basically, expectation, what does it mean? So for a random variable, when you try to compute the expectation, so it is basically the weighted average of the probabilities. So you would be getting an exact value of how much you can improve, based on which you can try to choose the point. So here you can see instead of looking at the improvement, just this random variable, we are taking the expectation of this random variable, which is a weighted average. And based on that, we will be taking the next potential point, which we are supposed to explore. So here is the formula. So based on which this expected improvement can be calculated. So here you can see this first part, phi of z is the CDF, and the second part, phi of z, is the PDF. So it is taking into account both the PDF as well as CDF. And the second part is taking into account the variance, right? And the first part is taking into account the mean. So we can control the behavior of how much importance you need to give to the first component and how much importance to be given to the second component based on this value epsilon. So when you increase this value epsilon, this first component will become negative. So you are giving more importance to the second term, that is variance. How can you interpret this thing is, in the previous diagram, when you increase the epsilon value, you are trying to give more importance to the second term. What does that mean is, you are giving more importance to the areas where the variance is more. So here, you have 3 regions where the variance is highest. So you try to give the importance to these 3 regions, and you try to explore these regions by choosing some point in the search space. When you decrease the value of epsilon, then you are giving more importance to the mean. That is exploitation. So you have already found out this particular potential point which has the highest accuracy. So when you reduce the epsilon value, it is giving more importance to the first term. That means it will try to exploit the current maximum and try to sample the points which are close by to the current maximum. So usually the assumption is the maximum, like the current maximum, whatever you have achieved till now, the global maximum would be like at a very small distance with respect to the current maximum, like either the positive side or the negative side. So that is the exploitation, which is taken care of in this particular term. So here we are taking the trade-off of exploitation as well as exploration based on this epsilon parameter. Any questions on this?
Can you also change that epsilon? So
Yeah,
that it
this is a
starts-
tunable parameter. So this
Yeah.
basically this parameter will entirely control how well the acquisition function is able to choose the next point as quick as possible. So you can basically try with different experiments and try to choose it so that the trade-off is maintained between exploration and exploitation.
And can it
Usually-
also change with, yeah, my question is, can it also change within the same experiment? That you start with a smaller number and then change it to a larger number?
Yeah.
Or-
Yes.
Okay.
I'll show that during the code walkthrough.
So you basically need to tune a hyperparameter to find other hyperparameters.
Yeah. Yeah. So there are an advancements on these acquisition functions where there is no need to choose any hyperparameter at all. I'll discuss that a bit later. So this is this third acquisition function, that is upper confidence bound. So here this function's formula is defined very simply. It is just this mean plus a constant multiplied with a variance. So this mean and variance are the values that you get from the Gaussian process. So here the surrogate model Gaussian process, which is represented in the right line. So you get based on the Gaussian process regressor, like whatever based on these red points, right, observed data. You can see there are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 observed points till now. And based on these 8 points, this Gaussian process regressor has fit this particular line. So right now we have fit for all these 8 points. So how to proceed further, like which point to choose next is defined by this particular formula, that is mu plus lambda times sigma. So we derive this mu and sigma from this Gaussian process that has already been fit, and try to fine tune this lambda parameter. So this lambda works out similar to the epsilon in the previous acquisition function. So you try to vary this lambda value and choose the best value based on which works out the trade-off is best maintained. So here I have chosen lambda equal to 5. So I have chosen it as a greater value, right? So when lambda value increases, you are giving more importance to the variance. That means you are trying to explore the unexplored regions. So here you can see the acquisition values function, how it is changing. So only for these unexplored regions where the variance is highest, you are getting the acquisition function, the peak value. So obviously here I would choose this particular point where the acquisition function is highest and try to get the next training point. So that is how it will look like. So this will explore more. So even though it has found this particular point, which is the current highest, it is not choosing some point nearby this current highest. Instead, it is choosing a different thing because of the lambda value. So if I choose lambda equal to 0.2, very less value, I'm giving more importance to the mean. What this means is the current maximum that has been already achieved is the mean, right? So I try to explore the next point based on the already observed maximum. So here you can see the acquisition function, how it is varying. Now it is when you can compare the difference over here itself. So when lambda was 5, you can see the peak was happening at the unexplored part. When the lambda was just a small number, you can see the peak is happening at the already current best that you have achieved till now. So this is exploiting more. So you want to fix the value of this lambda such a way that it will explore as well as exploit. You are not supposed to do that either of them only. So you are supposed to maintain the trade-off between both of them. So when it is kept at 1.2, here you can see the acquisition function. It is highest at unexplored regions, and it is also highest at the already explored regions. So this maintains a good balance between the exploration as well as exploitation. So this is how you need to tune the lambda parameter, epsilon parameter in these acquisition functions. Did your doubts get clarified, Stephen?
Yeah, I'm good.
Okay. So this is the last acquisition function that we'll be talking about. So this is the most simple and the most reliable acquisition function. So here there are no hyperparameters at all that you are supposed to tune, and it is a very simple approach. So what here I'll be doing is, so suppose this black point represents the already explored region training point, and I have fit the Gaussian process based on this particular point. So you see this black line represents the posterior mean or the Gaussian process currently. So now how I choose the next potential point where I want to explore is, I try to sample the realizations from this Gaussian process. So it is similar to what I showed here. So here I have the Gaussian process defined in these bounds. And when I try to sample the Gaussian a realization, you see each of these realizations are within these bounds, right? This is analogous to Thompson sampling. So I just try to derive or sample a particular realization from the already fit Gaussian process. So here I am sampling 3 functions from the Gaussian process. So here you can see all these 3 functions are within the upper and lower confidence bounds. So this is 95% confidence bound. So you might be getting some of these sampled functions beyond these bounds at like 5% of the times. So when I sample a few functions from this already fit Gaussian process, what is the current maximum that I get over here where the variance is more? I try to choose that particular point to explore for the next search phase. This is how this Thompson sampling will work out. So you try to just find out the maximum location of these 3 samples and try to choose that particular point as a potential point for the next iteration. So compared to the previous acquisition functions, this Thompson sampling will try to learn where the maximum is present in very minimum number of iterations. And it is very simple function that can be executed as well. Any questions over here?
No.
Okay, I'll hand it over to Kirtana for now.
Yeah. Okay. So Shreyas, you want me to share the screen?
Your wish. I guess that's better.
Huh.
Stop.
Okay. Let me quickly share the screen. Yeah. So Shreyas has nicely explained all the ingredients that we are going to use for Bayesian optimization. So what exactly is Bayesian optimization? Like so far we have discussed about the acquisition functions and objective function and surrogate model and all. So how Bayesian optimization is gonna be different from grid search or random search is like this is because this guy keeps track of the things, like whenever we are trying the grid search or random search. So what happens is we specify the range, and internally the grid search or random search doesn't keep track of the evaluations it does. Whether the particular error function or any function like it is trying to optimize, it is getting optimized or not, it just keeps spitting the numbers like whatever the range we have specified. So that is the uniqueness of Bayesian optimization. So how internally it works is, so it basically builds a probability model of the objective function and uses it to select the hyperparameters. So here, let us take an example like for random forest regression model. So it will be easy to relevantly compare it with the objective function and all. So since it is a regression model, the function will be root mean squared error. So what we will do is like what Bayesian optimization does is it uses the objective function and then it tries to build the probability model for that. And what it does is like it takes the set of hyperparameters and then make sure the objective function is getting minimized. So how it does that is it again keeps tracks of the things. So the example is this, like random forest, and then the function is RMSE. So the function that we are that is used to compute the RMSE is the objective function. So what exactly it is the function that is going to be in place of the objective function, that the initial one that the Bayesian model is going to assume and then start with the Gaussian distribution and samples. That is the surrogate function. So if we know the distribution, the process is very easy, right? Like we know the distribution, so obviously we'll use gradient descent or some other method, and then we'll go with finding the global minima. But here the distribution is something which is not known initially, and we'll make use of Bayesian optimization with the probabilistic model and fine tune the parameters. I mean, find which one is basically helping our objective function. So the diagram that you see on the right side is the steps that we'd have, steps which Bayesian optimization takes. So first thing is like we observe the data points and then we build that surrogate model. So after the basic model is built, we maximize the acquisition function. So this acquisition functions like will be one of the things from what Shreyas has discussed. And we'll sample the next point. And based on this evaluation, we'll update the surrogate model and the process repeats. So this is the entire life cycle of Bayesian optimization. So yeah, the same thing is mentioned over here. Like it keeps track of the past evaluation results, and every time when it gets the parameters, it just apply these parameters to the true objective function. I mean, true objective function is nothing but the RMSE function, and then it sees like whether it is helping or not. Then it will update the surrogate model incorporating those results. So again, it will repeat till the particular function is minimized. In case of classification, it will be accuracy, so it will be maximized. So any questions on this, like the entire process, because this is the thing like very important.
No, it's clear.
Yeah, thanks to Shreyas. I think he has nicely explained all those things. So now after discussing this topic, before knowing that, like now it is very clear. Cool. Okay. So this is just the sample, the diagrammatic representation of what we have said so far. So this distribution is something which we don't know initially. So obviously we'll go to the help of Gaussian distribution and we'll assume this. So first, they have, we don't know all the points in that, right? Like we just have taken only 10 samples out of it. 10 samples is nothing but like 10 set of hyperparameters, and it is trying to understand the distribution with that. So what will happen when we want to add the next, we have to find the next one is, so we'll obviously build a surrogate model with that. So the blue line here is the model, and the blue color shade you see is that deviation of the distribution that it come across. Yeah. So how we will go for the next point is like we just see which one is helping our particular function. I mean our particular objective function. So when the new set of hyperparameters come, we see like whether it is what set of hyperparameters is helping the acquisition function to be maximized, and that will be taken. And what happens is we'll take that and then put it on the true objective function and see whether it is actually doing a magic or not, and then we'll keep track of it. So that what will happen is the surrogate model is getting updated each and every time, and this set of evaluation can be happening for I mean there should be a limiting factor, right? Like when it needs to be stopped or something. So we can specify the number of evaluations because this thing I think we have already discussed in daily also. So what happened was when I was experimenting with the intent classifier model. So initially the number of evaluations, right? Like even though the number of evaluations will be like increasing, like let's say 100, 200, 500. Once the particular maxima or minima value has been found, it is not going to like improvise over that. So that is the limiting factor for that. Like once the particular function is optimized, then it is anyways going to result the same set of hyperparameters. How many times you run or beyond that limit. This is the comparison between grid search and random search and the hyperopt library which we use for Bayesian optimization. So these are the three models: logistic regression, SVM, and random forest. So I did not want to add the parameters and all because anyways that is not needed. So you can actually see the numbers like when we have fine-tuned it with Bayesian optimization, how it has improved. And this SVM is the one Stephen was telling yesterday, like performing in pair with the deep learning model. So this random search and grid search really took a long time. Actually, we have been specifying the range for over a week and fine-tuning it, and hyperopt did the magic in like some 2 hours.
Basically, random search and grid search are just a bit better than trial and error method, but almost they are same only.
Yeah. So the thing is, like, we can't guess the ranges. I mean, like, we have worked with one text data set, like for summarization or something, and we can't guess the same range for others because the word vectors, right? Like it also
as data changes, everything will change. And here you can see there is no overfitting at all that you need to take care of. It is taken care of in build.
Yes. So this is the experimentation result, and next what we are going to see is the code walkthrough plus demo. I'll just pass it over to Shreyas. I'll stop sharing.
Okay. So here in the code walkthrough, there are 2 things that I'll be discussing. So the first thing is suppose this is a example of, I guess this one I had showed it before. The objective is to find out the location where the gold content is maximum. Okay, so so this distribution is unknown. Like this is a ground truth, but anyways, we don't know how this looks like before. So here our first experiment is to find out how this distribution will look like using all these techniques that we have seen already. So what we do is we use this Gaussian process, and so this blue function is the ground truth which we do not know. So we try to model the blue function with the help of Gaussian process that is defined with these confidence bounds and the black line which represents the mean. So right now, without any explorations, without any training points, so we see it is a flat, uniform kind of a distribution. This is a prior model. So later on, we try to explore each and every point and find out the gold content, and we try to move upon the next point which we need to choose so that it will maximize the gold content with respect to the already explored point. So here you can see how it is varying. So first point is known, and the first point was chosen at x equal to 0.5 location, and the gold content was somewhere around 5.5. So based on this one training point, the surrogate model of the Gaussian process has fit so that it will pass through this point. And later, we try to explore other points and try to fit this Gaussian process almost similar to the ground truth function. So here you can see as number of iterations or number of explorations at different locations, you are almost fitting the ground truth function only. So in the first question, the basic agenda was to find out the distribution. It's not like I did not tell like what is the location where the gold content is maximum. That's not my objective to find out. I just want to find out what is the PDF or the distribution of the gold content. So here there is no need to maintain that exploration or exploitation trade-off. So since I'm not bothered of where the maximum location is. So here I'm just trying to plot this distribution curve. So here I'm just trying to explore. There is no exploitation over here. So exploration is just like try to choose the next point where the variance is highest, and try to compute the gold content over that particular point. So here you can see all these iterations. There is just pure exploration. There is no exploitation that is happening. So ideally, if there was a trade-off, since this particular region was the highest with the gold content, it should have explored many points in this particular region. But since this is a problem of just fitting the distribution of the curve, we are just exploring instead of exploiting. And coming to the second question, that is what is the location of the region where the gold is maximum? We try to use the multi-arm bandits approach with the acquisition functions that have shown before. So this first thing is the upper confidence bound. So I guess this acquisition function you can see over here. I have defined I'm taking the mean and variance. So I guess the formula I had shown mu plus lambda times sigma. So I'm taking the mean and variance from the Gaussian process, GP. And later, this formula you can see the same that as I had shown before, mu plus lambda times sigma. So using this function, we try to find out the acquisition function and choose the next point as the one which is giving the maximum acquisition value. So here you can see with the lambda equal to 10, it just, since it is more, it just tries to explore instead of exploit, since the lambda value is more and it gives more importance to the variance. So here you can see it is just purely exploring. So here you can see like even though the maximum gold content was this, in the next iterations it just moved away from this maximum content because lambda value was more. So with the 12 iterations, you can see almost more than 50% was invested in different locations, even though it knew the potential location was this particular thing. So that is using UCB. So using probability of improvement. So this is the PI function. So this is basically like the CDF of the probability distribution curve, which is lying above the current maximum, right? So I have just written it down over here, the CDF of Z. Here you can see how it is varying with respect to the acquisition function and the epsilon value. Here with the epsilon equal to 3, it is trying to explore. Yeah. So ideally this epsilon, if I had reduced a bit, it would have exploited as well. The third thing is the expected improvement. So here from the formula that I showed, it is a combination of the CDF as well as the PDF. The first term is exploitation term and second term is the exploration term. And based on that, you can see the variance. So whatever the point that has been already explored, you can see the acquisition function value is dipping to the lowest because already you have explored and the variance is less. So you can see all these kind of peaks which are going down, which represents that the acquisition function is less as the variance is less. Yeah, and the last one is Thompson sampling. So here there is no parameter or no formula as such. So you already have the Gaussian process that has been fit for the training samples that you have observed till now, and you just try to sample a particular function from the already fit Gaussian process. So here you can see I'm just sampling from the posterior distribution. So here size equal to 1 means that I'm just sampling one realization out of this particular Gaussian process. But if I increase this number in the PPT, I guess you have seen that there were 3 samples in that particular bounds. So that means like here, if you give this size equal to 3, then it will sample 3 realizations in that bounds and tries to choose the point which is giving the maximum value from these 3 samples. So here it is just taking the maximum value of the one sample. If you the number of samples as it increases, the more quick is the convergence. So here you can see it has observed that the maximum point is here at the 6th iteration. From then you can see it is trying to choose points nearby that location many times. So here it has chosen almost 4 or 5 times consecutively. It is just trying to exploit, since it has learned that this is a potential location where the maximum would be present. Coming to the random sampling, so this is just like a random search without any strategy, just pick out something out of all possibilities. So you can see the acquisition function, which was very smooth with all other like algorithms. So here in random search, you can see how messy or noisy it is. So when I plot this comparison of all these acquisition functions, you can see the random process, like the random algorithm. It was able to achieve this particular value only, the maximum gold content of this particular value, and after that it got saturated. It did not improve because it is not learning from what it has already explored. For other different acquisition functions, you can see the improvements. So here usually the UCB and the Thompson sampling, you can see the maximum that has been achieved with respect to the true objective function. Any questions on this?
Yeah, could you explain it using one of these graphs, but then where instead of having just one hyperparameter, because basically you're just checking the drilled sites, how would this look if you would have 2 or more?
Are you saying like for if you use some SVMs or random forest, like right? How it would look like?
Well, more like how would this would look if you would explore more options. So let's say in this example you would explore both drilled sites and type of machine to use or whatever.
Oh, okay, I understood. Like you're asking like if right now there is only one variable x based on which you are trying to search.
Yes.
So you're asking like if we have multiple variables, how we are going to search, right?
Yeah, exactly.
Yeah. So if we have multiple variables, similarly, like suppose SVM or random forest, we are having multiple hyperparameters, and there is one such combination of those multiple hyperparameters for which the objective function will be the maximum, or like the loss function will be the minimum, right? So over here, since this is a one variable, you can visualize this in a 2D, but if you have 2 variables, it will be a 3D, and beyond that you can't visualize as such. I have one such example given. I guess I'll showcase that to you so that you'll remember. Sorry, which one it is? Okay, yeah, SVM. Yeah, so here you can see this is a 2D graph. Here there are two hyperparameters, C and Y. Here you can see, right, hyperparameter 1 and 2. So for a combination of these two hyperparameters, this is the global maxima, and this is how the curve, the graph looks like. The z-axis might be the accuracy. So here you can see the color code for which the values are ranging from. Like this is how it will look like if you have multiple parameters.
Yeah, then it makes sense indeed.
Suppose here if I try to change this, here you can see the exploration and exploitation that is happening with the number of iterations. So here it has chosen these 2 points. It is coming closer. It's not that it it will be able to achieve the global maxima all the times, but it tries to come closer as much as possible.
Yeah, so that means that these algorithms always explore the hyperparameters as a set and never individually.
No, not individually, because this is like these hyperparameters together. When you combine, you get the result, right? It's not like an individual hyperparameter. There is a lot of correlation between these hyperparameters, for which you'll get the minimum or maximum value of the objective function.
Okay, thank you.
Yeah. Any other questions? Okay, that's it from my side then.
Nice. Thanks for the presentation. I think you guys broke a new record in terms of the longest Let's Learn.
1 hour 23 minutes.
What I think was really nice about this one is that she gave some